Today I will talk about heterogeneity at the tumor microenvironment level. Sorry about the font. But everyone knows about tumor heterogeneity, but what does that really mean? So it used to mean that no tumors are alike because every single tumor would have distinct collection of drivers and passenger genes. But soon people realized that even within one individual, within one single tumor, different regions of the tumor may have different patterns of mutations, leading to the intra-tumor heterogeneity, causing the difficulty in treating tumor. So based on the early understanding of the tumor heterogeneity, we realized that we really need to understand tumor in a detailed fashion. We need to stratify tumor in a certain way that can match up with the current therapies. For example, right now there are different kinds of molecular classification, mostly based on the driver event. The driver event can be individual genes or different pathways or the whole transcriptome. So this will provide guidance for personalized therapies. Patients with EGFR mutation obviously receive treatment for EGFR inhibitors, but HER2 will receive treatment based on Herceptin. But this is the early understanding. But soon people realize that with the success of immunotherapy, people realize that the most successful target, like PD-1, is actually not on cancer cells. Those are in the tumor-infiltrating CD8 cells. Okay, so this really changed our way of thinking tumor studies, because for many years, tumor study has been reduced to the study of the cancer cells themselves. Okay, but when immunotherapy works, it works like wonders. You can, in some cases, even cure cancer patient, but the response rate to the immunotherapy response varies significantly, leading to the heterogeneous response rate. So different cancer types have very high response rate, but some others, like pancreatic cancer, sarcoma, would have very low response rate. Lots of effort had put in finding molecular markers for predicting such response rate. But without any definitive success, the most successful markers are tumor mutation burden and PD-L1 expression. But so we get to ask the question that what is the reason behind such a heterogeneity? When patients don't respond, what is the underlying reason? If you want to find additional markers or additional targets that make it more effective, should we keep on looking at the T cells, or should we look elsewhere? Perhaps within the tumor, there are other immune evasion mechanisms. We all know that immune evasion is one of the major hallmarks of cancer. So this is not working. Okay, this one's working. All right. So, but maybe there are multiple immune evasion mechanisms not related to CD8 T cell exhaustion, but maybe those are related to Tregs, dendritic cells, macrophage cells, T helper, or B cells, or in case of even fibroblast cells. So what is the answer? The answer probably lies into the tumor microenvironment. So the tumor microenvironment really refers to the whole collection of all the cells within the tumor. It's not a simple collection of cancer cells. So if you go back just a few years ago, we didn't know a whole lot about what's inside the tumor, including what are the specific cell types that really make up to the total collection of the tumor, and whether the cells would have any special fate, lineage, or dynamics, and how they interact among each other, and whether the cells will form special structures within the tumor, and how the cells collectively influence the clinical parameters, including how they respond to therapies. Okay, and so over the past now 10 years, my lab has focused exclusively on understanding some of the basic questions regarding the tumor microenvironment, mainly with the help of single-cell sequencing. So first we start with the basic composition of the cancer cell types. And so this is very important to understand what's really inside the tumor, because very often I compare this to the finding of the basic element in chemistry. So similarly, for tumor, we need to understand the periodic table for the cell types for the tumor, okay? So this is based on the collection of a large amount of work to show that over the years, we indeed found a number of cell types that seem to be more enriched in tumor based on the comparison of the cell composition between tumor, tumor core, tumor edge, adjacent normal tissues, lymph nodes, blood, ascites, among other tissues. Okay, so we can really quickly realize that exhausted CD8 cells indeed is enriched as expected, but so are other cell types like activated Tregs, PH1-like cell, the LAMP3DC cells we found, SP110, and others. For example, the LAMP3DC cells seem to be the mature form of both CDC1 and CDC2. When they got matured, they gain ability to migrate away from the tumor to the nearby lymph nodes, presumably activating T cells there. And from the colon cancer analysis, we found new subtypes of myeloid cells we call SPP110, which is very different from the conventional view of the M1, M2 scheme. Okay, this group of cells seem to have pro-tumor function. This group of cells is also seem to be important in the tumor metastasis process. Okay, but typically when we study a tumor indication, we start with a single tumor indication. For example, we initially found LAMP3DC from the liver tumor analysis. We found the LAMP3 SPP110 from the colon cancer analysis. But are these cells universal, or they are only unique to a particular cancer type? So this brings to the next important question that's related to the tumor heterogeneity. So we want to ask the question whether there are notable differences between distinct cancer types. And maybe if there are differences, and differences are stable enough, maybe this may influence how patients respond to immunotherapies. So one way to directly address this is to systematically compare tumor microenvironment features across cancer types using the similar platform. So we started with analyzing the infiltrating myeloid cells by studying 15 major cancer indications, and we found that some of the myeloid cells, like LAMP3DC, are universally found across all cancer types, as opposed to SPP110, which are only found in a subset of the major cancer types. So even when the cells seem to be universally present, their relative abundance seems to vary significantly. For example, LAMP3DC are much more abundant in nasopharyngeal carcinoma, stomach cancer, esophageal carcinoma, as opposed to breast cancer, kidney cancer. So indicating that these cells are probably more relevant in this cancer indication than these. Assuming that several years down the road, we are able to develop a new drug targeting this kind of cells, I would assume that the new drug will be more effective in this cancer indication than this. But in fact, if you expand this study to all T cells, we found similar kind of patterns. Exhausted T cells, which viewed to be universal by many labs, are actually also heterogeneous. Such exhausted T cells are highly abundant in cancer types like melanoma, some subsets of lung cancer, esophageal carcinoma, but lowly abundant in multiple myeloma, breast cancer, stomach cancer, okay? Partially explaining the different drug immunotherapy response rate. You can also find similar patterns for Tregs, or these are activated Tregs. Then we did an interesting experiment, which appeared to be simple, but I think has implications that are important. So typically, when you classify tumor, you take the tumor property, mostly cancer cell driving events, like expression patterns, driver genes like this. You can form different kind of molecular subtypes. But we ask the question, what if you remove the cancer cells altogether, and you only look at T cell compositions? And so we seem to be able to classify all tumors. This is 21 major cancer indications that fall into 8 categories. Melanoma, for example, largely fall into the CO2 categories, where they have a lot of exhausted T cells, but very low abundance of activated Tregs. So this actually is consistent with the notion that a lot of fraction of melanoma are more responsive to checkpoint blockade. We should treat the patients with a lot of exhausted T cells, but not a lot other immune evasion mechanisms, as opposed to thyroid cancer, which has fallen into three category, which don't really have a lot of T cell exhaustion features. So we think this gives us the encouragement that maybe we can rely on the immune cells to better classify cancer. But what we have learned so far is not enough. So this concept of using tumor microenvironment to divide those into different categories is not a new concept. In fact, many people have thought about this. For example, a review by Lieping Chen's lab suggests maybe the tumor should be classified based on the infiltration level of T cells and the PD-L1. So this may impact how patients respond to immunotherapies. But clearly, this kind of classification is probably too crude. We should look at the immune cell types in a more detailed fashion. So after we had collected all the cell types, we think that we should not really stop there. We should try to be ambitious and try to collect all those major cell types within the tumor. How do we do that? We keep on collecting new data for different cancer types and more cancer cell types. I want to give you a more recent example on the T cell. In this case, we took a pure data-driven approach. So without sequencing any of our own data, we decided to just download published data out there since there are the data are so abundant out there. So we end up collecting 71 data sets covering over 700 patients for 24 cancer types. We end up getting 160,000 individual NK cells. This appears to be large, but it's actually not a large number because in every single patient, you can easily get over 10,000 cells. So the absolute abundance of NK cells is actually very low. So if you were to sequence your own sample to get, and you're able to get like very small number of NK cells. So you're only able to get enough NK cells by doing data integration. So by integrating all the NK cells, we're able to find that NK cells also fall into several major subtypes. Each subtype may have different levels of utilization of cytokines and the regulatory molecules. And we found out that different cancer types also differentially use such NK cells in a reproducible way. And through this analysis, we asked the question whether we can identify the NK cell subtypes that seem to be differentially enriched in tumor. Then we were able to find one. So we call those tumor-associated NK cells or tank cells. Such tank cells are indeed highly abundant in tumor compared to adjacent normal and other blood locations. They seem to be located in the developmental later stage. And as the cells become NK cells, such tank cells, they gradually show the decrease of cytotoxicity, but elevate the expression level of inhibitory receptors and stress level genes. And by performing a series of bioinformatic and spatial transcriptomic work, we show that such NK tank cells would have very close interaction with myeloid cells and LAMP3DC cells. For example, here we show that the macrophage cells close to NK cells tend to exhibit lower level of activation marker CD86 and higher anti-inflammatory markers TGF-beta. So this actually give you a quick example about how we go about studying different kind of immune subtypes. But we keep on doing this for additional cell types. For example, we've done this for fibroblast cells. I don't have time to go through the details, but we found a lot of different subtypes which show their differential presence in tumor types. We've done this for B cells. Also, through pure data integration, we're able to find data for B cell, single cell data for over 1,000 patients. And these B cells also fall into different categories and different kind of tumor indications will have very dramatic patterns, different patterns of B cell usage. Okay, so based on this, we say, well, we have all those data together. How do we piece everything together to see we can have a more holistic understanding of the tumor microenvironment? So this is we take on a even more ambitious role about taking all the data together And so we require the data to be comprehensive, unsorted, and we end up getting data for over 1,000 patients, representing 24 major types. We have the major classifications, and then we put those into even small categories, and we're able to show that we can recapitulate that some of the immune cell types seem to be more enriched in tumor compared to others. Okay, then we say, well, let's, again, exclude the cancer cells altogether and just take the non-cancer cell types within the tumor to do an unsupervised clustering. So this is what we found. And so first of all, you look at the red bar here, that shows the total level of immune cells, or CD45 positive cells. So immediately we see that some of the immune cell types have a very low level of immune cells corresponding to those cold tumors. But not all cold tumors are alike. Some cold tumors have a higher abundance of those kind of CAFs, which I didn't have time to talk about. Some others have really a strong presence of endothelial subsets. And then you have some other cell types, like class number 7 and 10, they seem to have a lot of heavy presence of exhausted T cells. And those are probably the ideal patients for immune checkpoint blockade. But then you have other cancer patients which have a heavy presence of activated Tregs here. So those are corresponding to class number 4 and class number 10 here. Finally, we have some other cell types, tumor types, that don't have any strong T cell features, but instead, they have a lot of presence of tumor-associated macrophage cells. So this is based on what we call the holistic classification based on the TME. And so I think this gives you us a whole new dimension of the tumor heterogeneity. This would give us an indication how the different patients may use a different mechanism for immune evasion. And so this may have therapeutic implication because for cold tumor, we should try to find ways to really heat up the tumors. For those ICB, the patients with a lot of exhausted CD8 cells, those are the ideal candidates for the current immune checkpoint blockade categories. But for Treg patients, we should really find ways to deplete those Tregs, okay, or inhibit their functions. Similarly, for the TAM patients, we should find ways to inhibit such TAM cell types. So I'm going to go back to the finding of the cell types I described previously. So if we know how these different cells are related to immune evasion, maybe we should try to develop new therapeutic strategies. And for example, Tregs, obviously, we should try to maybe deplete such activated Tregs within the tumor. And for TAMs, we should also try to prevent the TAMs from forming or deplete such TAMs. Okay, similarly, we can work on the CAF to see how we can modulate CAFs to maybe change the temperature of the tumor. And so I'm going to essentially use a few slides to show our current effort. And in Champion Laboratory, we are pursuing some of the strategies here. But today, I'm going to quickly use two quick stories. For example, if you know that this is a cell type you want to work on, how do you find the right targets? Of course, you want to find the genes that are differentially expressed or highly expressed on those cell types. But that does not make the genes targets. For the target really means that the genes need to be specific in this cell types, but also they should be lowly expressed elsewhere throughout the body in other cell types. Got it? I will add your WeChat. Okay. So this requires a lot more data integration. So here, by working with the company A Biosciences, we are able to put everything together. We integrate even more data together, even more sort of all available single-cell data from mouse and human systems, so that we can quickly identify if a gene is specifically expressed in one cell type, but lowly expressed everywhere else, okay? And so through this exercise, we found that CCR8, for example, is a great target for activated Tregs, okay? And after you found this, of course, you can go through the antibody development. You can improve the affinity of this antibody through artificial intelligence. Then we can improve the antibody can make sure that your antibody has a higher affinity binding than other competing antibodies from Bayer and BMS. And then of course, using the in vivo model can show that adding the antibody will be effective in the mouse model. So finally, we say, well, cold tumor obviously is present one major barrier for some of the patients. And one important reason that some patients are cold tumor is the presence of a specific CAF subtype. And so the CAF can present both a physical and functional barrier to the tumor so that immune cells have trouble getting into the tumor. So we think that if you're able to find targets, molecule on these molecules, maybe you can find ways to heat up the tumor. So we can find specific genes for these CAFs. Then we can say, well, maybe we can design an antibody that specifically recognizes such CAF subtype. Then instead of killing such cells, we can add an immune-inducing cytokine that can attract other immune cells like B cells and other T cells. So we're able to do this, and we're able to show that adding such an antibody can actively recruit immune cells like B cells and T cells. And for well-known cold tumor like NPC, which is resistant to the current anti-PD-1 antibody, would be responsive to our antibody. Adding the gemcitabine will completely flatten the tumor growth. So let me quickly summarize that it is very important to study the tumor microenvironment. And we all know the tumor is heterogeneous. But when we, probably a lot of people have reviewed a lot of manuscript or listened to the talk, and then where they say, well, the final conclusion is that tumor is heterogeneous. Well, that's not a conclusion. We already know about it. So that should not be the conclusion. Instead, they should be decoded. We should find patterns. Once you have pattern, then you can find ways to attack each subtype separately. So we found that we were able to find tumor-specific cell types, and this can lead to new therapeutic target identification, as I showed. And also, more importantly, that different tumor types exhibit very strong tumor microenvironment differences. Such differences can eventually lead to personalized immunotherapies. I'll stop here. I want to thank lots of people listed here. And mostly, I want to thank Champion Laboratories' support for a lot of the work I presented today. Thank you very much.